When we set out to rethink our place in the universe, the first step is often the most surprising, because it forces us to confront how limited our everyday perspective truly is. From where we stand on its surface, Earth feels impossibly vast, an entire world that most people could never hope to traverse in a lifetime. Our continents stretch over thousands of miles, our oceans wrap around nearly 3/4 of the globe, and the tallest mountains appear to pierce the sky. Early civilizations naturally assumed that this immense environment was all there was, that the ground extended outward without end, and that the heavens were little more than a dome overhead decorated with flickering lights. That assumption makes sense when you consider what the horizon offers the naked eye, a flat expanse where the curve of the planet hides itself too subtly to perceive without gaining extraordinary altitude. Even when modern measurements tell us Earth spans roughly 7,226 miles across at the equator, and that circling it on foot, imagining one could walk across oceans, would take over 3 years of steady daily effort, this does little to prepare the mind for what happens once we step back and begin comparing our planet to the wider structures of space. The numbers certainly feel impressive, nearly 200 million square miles of surface area, enough that spending only a single second in each square mile would still trap you in the task for more than 6 years. Even one of the largest nations on Earth claims less than 2% of that terrain. Yet these statistics, as grand as they seem from our limited vantage point, begin to lose their weight the moment we take even a small conceptual step away from Earth itself. Because as soon as we zoom out, just a little, our planet's perceived immensity collapses. It stops dominating the frame and becomes merely one object among countless others. This effect becomes strikingly apparent when we consider the Moon, our closest celestial neighbour. Though it has accompanied Earth for billions of years and appears comfortably near in our night sky, the Moon is astonishingly distant in human terms. On average, it orbits about 238,855 miles away. Far enough that if you could somehow drive non-stop around Earth's equator 9.5 times, you would accumulate an equivalent mileage. The Apollo astronauts, racing toward it at speeds unimaginable in daily life, still required 3 full days to bridge that gulf. Yet the Moon itself is not insignificant in size. At just over 2,100 miles in diameter, it is large enough that, were Earth reduced to the scale of a basketball, the Moon would resemble a tennis ball. But this analogy hides the true scale of separation. The gap between the two worlds is so large that you could line up 30 Earths, end to end, in the empty space that divides them. This emptiness contradicts the compact depictions found in illustrations and textbooks, where the Earth-Moon system is often squeezed together for convenience. In reality, the two bodies float in a void that is overwhelmingly dominated by nothingness. It is our first clear hint that even within our own cosmic backyard, emptiness outweighs substance by an extraordinary margin. And while the Moon is uniquely large relative to its host planet compared to most moons in the solar system, so much so that some astronomers call the pair a double planet, its presence also teaches us that celestial bodies interact in subtle but profound ways. The Moon's gravity tugs at our oceans, generating tides that shape coastlines and ecosystems. It steadies Earth's axial tilt, preventing the wild wobbling that could otherwise produce chaotic climate swings. Even the near-perfect match in apparent size between the Moon and the Sun as seen from Earth, which allows for breathtaking total solar eclipses, is a coincidence produced by the fact that the Moon is about 400 times smaller than the Sun, but also 400 times closer to us. And this companion of ours is drifting away gradually about 1.5 inches per year, meaning that in Earth's distant past it loomed much larger in the sky and shortened our planetary day to only a few hours. For now, however, it remains our closest stepping stone into space, and a reminder of the ingenuity humanity displayed when it managed to set foot upon another world in 1969. Yet even the Earth-Moon relationship, extraordinary as it is, cannot shield Earth from the humbling truth that emerges when we shift our attention outward once more. Because immediately beyond the Moon lies the Sun, and in comparison to our star, Earth's proportions shrink to near insignificance. The Sun is not merely larger, it is so incomprehensibly vast that it challenges the limits of visualization. And it is here, as we transition from our familiar world to the immense scale of our star, that our journey into cosmic perspective truly begins. When we turn our gaze from the Moon toward the blazing heart of our solar system, the contrast in scale becomes almost disorienting. as if the mind is being forced to stretch far beyond its natural limits. The Sun is not merely larger than anything we've considered so far, it is the gravitational anchor, the furnace, and the architect of our entire planetary neighbourhood. Yet before humanity understood its central role, people believed Earth held that privileged position. The sky's daily rhythms, sunrise, sunset, the predictable sweep of stars convinced ancient observers that everything revolved around us. But once thinkers like Copernicus and later Galileo dared to challenge this deeply rooted intuition, the truth began to emerge. Earth was not the still point of creation, but a small sphere circling an enormous seething star. Understanding the Sun's scale is essential to understanding the Sun's authority. With a diameter of about 864,000 miles, it dwarfs Earth by a factor of 109. More staggeringly, its volume could engulf roughly 1.3 million Earth-sized planets, meaning that every continent, every ocean, every mountain range, and every person who has ever existed occupies a space that would barely register within the Sun's vast interior. Even this immense physical presence represents only part of the Sun's dominance, for it holds 99.86% of all the mass in the solar system. Everything else, from giant planets to dust grains, collectively forms a cosmic rounding error. Its gravitational pull dictates the motion of every world, including our own, as we circle it at an average distance of 93 million miles, a span so immense that even light, moving at 186,000 miles per second, takes over 8 minutes to travel from the Sun's surface to Earth. If the Sun were to vanish instantaneously, an impossibility of course, we would drift onward in darkness, unaware of its absence until those 8 minutes of light ceased arriving. Consider the human-scale equivalent. A car driving at highway speed would need nearly 2 centuries to cover that same distance. Yet for spacecraft like the Parker Solar Probe, engineered to endure extremes no living creature could survive, the journey still consumes months, even though the probe slingshots through space at speeds exceeding 400,000 miles per hour near its closest approach. Despite all this grandeur, the Sun is classified as a perfectly ordinary G-type main sequence star, neither exceptional nor rare among the billions scattered across just our galaxy. It sits comfortably in middle age at about 6 billion years old and will continue burning hydrogen for another 5 billion years before transforming into a red giant. What keeps it shining is a process both elegant and violent: nuclear fusion. Every second, the Sun converts roughly 600 million tons of hydrogen into helium, releasing energy that radiates outward across the solar system. In a single second, it emits more energy than human civilization has produced throughout its entire existence. Its surface roils at nearly 10,000 degrees Fahrenheit, while its core reaches temperatures of about 27 million degrees and compresses matter under pressures hundreds of billions of times greater than Earth's atmospheric weight. This churning engine powers not only light and warmth, but also unpredictable eruptions, solar flares, and coronal mass ejections that can fling charged particles across millions of miles. When these particles brush past Earth, they paint luminous auroras across polar skies, but powerful bursts can disrupt satellites, electrical grids, and communication systems. Gazing at the Sun through proper filters, of course, confronts us with the fact that Earth orbits something unimaginably more massive, more energetic, and more essential to our survival than any other object we know. Humanity's resistance to accepting this truth lasted centuries, because the idea that we are not at the center felt almost insulting to the ego of our species. And yet the revelation was liberating. It marked our first major step toward understanding the cosmos as it truly is, not as it appears from the surface of one small world. Recognizing that Earth circles the Sun rather than commanding it was revolutionary not only for science but also for philosophy, because it revealed our place was not one of cosmic privilege, but of cosmic modesty. As we continue outward, this theme deepens. Moving beyond the Sun's immediate influence, we encounter the rest of the inner solar system, a collection of scorching, cloud-choked or frozen rocky worlds that remind us how precariously rare Earth's conditions are. But before exploring those planets in detail, simply dwelling on the difference between Earth, the Moon, and the Sun prepares us for what comes next. The realization that with each additional layer of scale we examine, Earth shrinks not just physically, but conceptually, becoming less and less central to the great architecture of the cosmos. And yet that shrinking does not diminish its significance. It enhances our appreciation of just how extraordinary it is that a tiny, fragile planet can host the only known life in the universe. This juxtaposition of smallness and rarity will guide us as we move farther outward into the solar system and encounter worlds that reveal both the diversity and the desolation that define our cosmic neighbourhood. As we pull our focus away from the sun's overwhelming presence and begin surveying the inner solar system, we encounter a set of rocky worlds that, while sharing broad similarities in composition, differ so profoundly in their conditions that they highlight just how precariously balanced Earth's habitability truly is. Mercury, the innermost planet, presents a stark example of a world shaped by extremes. With almost no atmosphere to insulate or protect it, the planet's surface is battered relentlessly by meteorites and scorched by the sun's radiation. Temperatures swing violently, soaring above 800 degrees Fahrenheit under direct sunlight before plunging to nearly minus 300 degrees on the night side. Its slow rotation creates a situation where one day on Mercury lasts twice as long as its year, twisting any intuitive notion of time into something foreign. A little farther out lies Venus, a planet close enough in size to Earth that early astronomers imagined it might harbour oceans, greenery, or even life. Instead, Venus is a cautionary tale in planetary evolution. Its atmosphere, thick with carbon dioxide and cloaked in clouds of sulfuric acid, traps heat so effectively that the surface temperature remains around 900 degrees Fahrenheit hotter than Mercury despite being farther from the Sun. The atmospheric pressure is crushing, more than 90 times that of Earth's, equivalent to being submerged 3,000 feet beneath the ocean. Venus rotates slowly and in the opposite direction of most planets, likely the result of a long ago catastrophic impact. Its day lasts 243 Earth days, meaning the sun rises in the west and sets in the east, completing a world so alien that it defies familiar comparisons. Past Venus lies our own world, a rare sanctuary of mild temperatures, liquid water and protective atmosphere. But just beyond us is Mars, a planet that appears deceptively familiar. Mars boasts frozen polar caps, dusty plains, towering volcanoes and canyons that dwarf anything on Earth. In its ancient past, rivers flowed across its surface, lakes collected in basins, and perhaps even oceans spread across its lowlands. Yet today, Mars is a frigid desert, its thin atmosphere providing little warmth or protection. Average temperatures hover around minus 80 degrees Fahrenheit, and the surface pressure is so low that liquid water cannot persist for long. It either freezes or evaporates immediately. The question of what happened to Mars has long intrigued scientists, and the answer lies in its interior. Smaller than Earth and cooling more rapidly, Mars eventually lost the molten core necessary to generate a magnetic field. Without that magnetic shield, the relentless solar wind gradually stripped away its atmosphere over hundreds of millions of years, leaving behind the barren landscape we see now. Two tiny moons, Phobos and Deimos, likely captured asteroids, circle the planet. Phobos orbits so closely that it crosses the Martian sky 3 times each day, and is slowly spiralling inward, destined to break apart or crash into the planet within 50 million years. This inner region of the solar system, though compact compared with the outer realms, highlights the delicate interplay of distance, atmosphere and internal structure that determines a planet's fate. While Mercury is scorched and airless, Venus suffocates beneath a runaway greenhouse effect, and Mars has become a frozen relic of a once more promising world. Even as Earth stands out as a remarkable exception, its membership among these rocky planets offers a reminder that our planet's stability is not inevitable, but the result of fortunate circumstances. Moving outward from Mars, the boundary between the inner planets and the giant worlds beyond is marked by the asteroid belt, a vast expanse containing countless rocky fragments left over from the early solar system. Contrary to cinematic depictions of densely clustered rocks, the asteroid belt is mostly empty space. The objects within it are separated by vast distances, and a spacecraft could pass through without ever glimpsing an asteroid up close. The largest of these bodies is Ceres, a dwarf planet roughly the width of the American state of Texas. Observations by NASA's Dawn mission revealed bright spots in its craters, evidence of briny subsurface water that may occasionally seep upward and freeze on the surface. Such discoveries hint at the complex histories even small worlds can possess. With this belt of planetary remnants serving as a transition zone, we stand on the threshold of the outer solar system, a region dominated by massive gas and ice giants, whose scale and structure represent an entirely different chapter in the story of planetary formation. Before we journey into their vast atmospheres and moons, the inner planets remind us of a sobering truth. Habitability is fragile and rare, shaped by countless variables, and Earth's ability to support life is not merely a cosmic lucky break, but a delicate equilibrium that could easily have unfolded along a far more hostile path. Crossing the boundary beyond Mars, our journey carries us into the transitional region of the solar system, where small, irregular remnants of planetary formation drift silently in vast, sparsely populated space. This is the asteroid belt, a region often imagined as a chaotic maze of tumbling rocks, but in reality so spread out that a spacecraft could travel millions of miles without passing within sight of a single object. The belt contains millions of bodies, yet their combined mass is less than 4% of our moon's mass, making it more of a symbolic relic of the solar system's youth than a substantial planetary domain. Among these remnants, Ceres stands as the most notable, its nearly spherical shape granting it dwarf planet status. Measuring about 588 miles across, it is large enough to have differentiated into layers and may even harbour a hidden subsurface ocean with more fresh water than all of Earth's lakes and rivers combined. NASA's Dawn mission revealed intriguing bright deposits, likely salt left behind as briny water seeped upward and evaporated, suggesting that even such small worlds can conceal geologic and possibly chemical activity. Leaving the asteroid belt behind, we enter the realm of the giants, beginning with Jupiter, a world so massive and influential that calling it the king of the solar system is almost an understatement. Jupiter's diameter stretches nearly 87,000 miles, making it over 11 times wider than Earth, and its volume could engulf more than 1/300 Earths, yet its impact extends far beyond sheer size. Jupiter's enormous gravity shapes the architecture of the entire solar system, redirecting comets, capturing wandering asteroids, and potentially shielding the inner planets from catastrophic impacts. Some researchers believe Jupiter's stabilizing influence may have helped create the conditions necessary for complex life to emerge on Earth. The planet's most iconic feature, the Great Red Spot, is a storm larger than Earth itself, spinning with winds approaching 400 miles per hour. This swirling vortex has raged for centuries, although modern observations show it slowly shrinking, hinting at long-term atmospheric changes. Orbiting Jupiter are dozens of moons, at least 95 known so far, ranging from tiny captured rocks to immense worlds rivaling planets in complexity. The four Galilean moons, Io, Europa, Ganymede, and Callisto tell four entirely different stories. Io is the most volcanically active body in the solar system, constantly resurfaced by the eruptions triggered by Jupiter's intense tidal forces. Europa's smooth, icy crust hides a global ocean beneath, an ocean that may contain twice as much water as all of Earth's oceans combined. Ganymede, the largest moon in the solar system, surpasses even Mercury in size and possesses its own magnetic field. Callisto, heavily cratered and ancient, preserves a record of impacts stretching back billions of years. Beyond Jupiter lies Saturn, nearly as large but distinctly more elegant. With a diameter of about 72,000 miles, Saturn could hold more than 700 Earths within its volume, yet it is its rings, frozen shards of ice and rock, that give the planet its unmistakable aura. These rings extend tens of thousands of miles outward, while remaining astonishingly thin, in many places no thicker than a few dozen feet. Their origin is still debated. They may be ancient remnants dating back to Saturn's formation, or the relatively recent debris of a shattered moon. Saturn's moon system rivals Jupiter's in richness. Titan, the largest, is the only moon in the solar system wrapped in a dense atmosphere. Slightly larger than Mercury, Titan's nitrogen-rich air is thicker than Earth's, and its frigid surface hosts rivers, lakes, and seas as of water, which is frozen solid, but of liquid methane and ethane. Titan's hydrocarbon cycle, with rainstorms and flowing channels, is eerily reminiscent of Earth's water cycle, making it one of the most intriguing places in the solar system. Another remarkable moon, Enceladus, though only about 313 miles across, hides a global ocean beneath its icy crust. Geysers at its south pole erupt with jets of water vapor and ice crystals, carrying organic molecules into space. These plumes, sampled by the Cassini spacecraft, suggest that Enceladus possesses the three essential ingredients for life as we know it: liquid water, chemistry, and energy. Continuing outward, we reach Uranus and Neptune, the ice giants. Uranus, tilted dramatically on its side with an axial tilt of nearly 98 degrees, experiences seasons that last over 40 years each, with one pole bathed in continuous sunlight while the other lies in darkness. Its pale, featureless appearance hides dynamic atmospheric processes, and its unusual magnetic field is offset and inclined relative to the planet's rotation. Neptune, the outermost major planet, is a deep blue world whipped by the fastest winds in the solar system, reaching up to 100 to 200 miles per hour. Storm systems appear and vanish unexpectedly, such as the Great Dark Spot observed by Voyager 2 during its 1989 flyby, only to disappear when later missions attempted to study it again. Neptune's largest moon, Triton, orbits in the opposite direction of the planet's rotation, a clue that it was captured from the Kuiper Belt rather than formed in place. Over billions of years, Triton is slowly spiraling inward, destined either to break apart and form a ring system or crash into Neptune itself. This sweeping tour of the inner and outer planets reveals the solar system as a tapestry of extremes, a collection of worlds sculpted by distance, gravity, and chance. Earth, nestled in a narrow band of habitability, stands out not because it is large or dominant, but because it alone supports the delicate conditions that allowed life to flourish. And as we prepare to journey beyond Neptune into the icy frontier of the Kuiper Belt, Earth's uniqueness grows ever more pronounced against the widening cosmic backdrop. Beyond the orbit of Neptune, the solar system transitions into a realm that feels less like a structured planetary system and more like an ancient frozen archive region, where the leftovers of creation drift quietly through an expanse so broad that even calling it a belt feels misleading. This is the Kuiper Belt, a vast ring of icy bodies stretching billions of miles from the Sun, populated by countless fragments that never coalesced into a major planet. Unlike the asteroid belt, whose rocky occupants are the shattered remnants of unrealized worlds, the Kuiper Belt is a repository of primitive material, containing objects that have remained largely unchanged since the earliest days of the solar system. Pluto, once classified as the 9th planet, is the most famous inhabitant of this domain. With a diameter of just under 500 miles, Pluto is far smaller than Earth's moon, yet its surface reveals a surprising complexity: towering mountains made of solid water ice, sprawling nitrogen plains, and thin hazes in its tenuous atmosphere. The iconic heart-shaped region, known as Tombor Regio, hints at internal activity, suggesting that even this distant dwarf planet may harbour subterranean layers or partial oceans warmed by residual internal heat. Orbiting Pluto is Charon, a moon so large relative to Pluto that the two bodies orbit a shared centre of gravity located outside Pluto's surface, forming a genuine binary system unique among major solar system bodies. New Horizons' 2015 flyby unveiled landscapes of unexpected youth and variety, revealing that even in the outer reaches of the solar system, geological processes can persist. But Pluto is just one member of a diverse population. Other large Kuiper Belt objects, Eris, Makemake, Haumea, each exhibit their own peculiarities, from high albedos to elongated shapes to rapid rotations. These dwarf planets demonstrate that the outer solar system is not an empty afterthought, but a complex frontier rich with cosmic relics. And yet, the Kuiper Belt is only a prelude to something vastly larger and more mysterious. Far beyond its outer boundary lies the hypothetical Oort cloud, a spherical shell of icy bodies enveloping the solar system at distances so immense they defy intuitive comprehension. The Oort cloud begins perhaps 2,000 astronomical units from the Sun, about 2,000 times the distance between Earth and the Sun, and may extend outwards nearly 2 light-years. This means the Oort cloud stretches halfway to the nearest star, forming an enormous bubble of loosely bound material surrounding everything we consider part of our solar system. No object in the Oort cloud has been directly observed, not because they aren't there, but because they are so small, so faint, and so unimaginably distant that detecting them is beyond the reach of current telescopes. We infer their existence from the behaviour of long-period comets, those that take hundreds or even millions of years to complete a single orbit. Their elongated paths imply origins far beyond the Kuiper belt, from a reservoir of icy bodies only lightly tethered by the sun's gravitational pull. Each time a passing star or galactic disturbance nudges this distant cloud, a few of these frozen wanderers fall inward, lighting up as spectacular comets when they approach the sun's warmth. The sheer size of the Oort cloud transforms our understanding of what constitutes the solar system. If we were to draw Earth as a small marble, the sun might be a grapefruit, the Kuiper belt a thin mist around it, but the Oort cloud would be a sphere spanning the size of a city. Within this enormous sphere, Earth sits incredibly close to the centre, drifting around the sun like a speck suspended in a cavernous cosmic cathedral. Everything we know, every planet, every moon, every asteroid, occupies only a tiny region near the sun's core. The rest is emptiness, broken only by frozen objects so distant they may orbit the sun only once during the entire existence of humanity. The existence of this cloud underscores just how immense the solar system is. When we speak casually of leaving the solar system, as Voyager 1 did in 2012, we really mean crossing the boundary where the solar wind gives way to interstellar plasma. Yet in a literal gravitational sense, Voyager hasn't even begun to exit the solar system. It would need tens of thousands of years just to reach the inner edge of the Oort cloud, and far longer to traverse it. This staggering immensity forces us to reconsider Earth's scale once again. Our planet, which once felt vast and all-encompassing, now occupies a space so confined relative to the true reach of the solar system that it becomes almost abstractly insignificant. And still, this is only the beginning of our journey outward. Soon we will leave the solar system entirely and step into the interstellar void, where the distances between stars stretch beyond any analogies we can easily construct. The Kuiper belt and Oort cloud mark the fading edges of the sun's direct influence, a final reminder that even on the fringes of our own stellar neighbourhood, we are dealing with scales that dwarf human imagination. Beyond these ancient icy borders lies the first star beyond our own, and with it, a new level of cosmic vastness. Leaving behind the frozen remnants that guard the outer boundary of our solar system, we now turn our attention toward the nearest stars beyond the Sun, a shift in scale so dramatic that even the vastness of the Oort cloud seems small by comparison. The closest star system to us is the Alpha Centauri triple system, anchored by Proxima Centauri, a faint red dwarf located about 4.24 light-years away. A light-year, the distance light travels in a year, is nearly 6 trillion miles, so Proxima Centauri's proximity is profoundly deceptive. It is our neighbour, only in a cosmic sense. In human terms, it is unimaginably remote. To give perspective, the Sun sits about 93 million miles from Earth, a span that light crosses in just over 8 minutes, yet Proxima Centauri is roughly 268,000 times farther away than that. If the Earth-Sun distance were compressed to a single inch, Proxima Centauri would lie more than 4 miles down the road. Even Voyager 1, the fastest and most distant spacecraft humanity has launched, drifting through interstellar space after nearly half a century of travel, has covered only about 15 billion miles, still nowhere close. At its current speed, it would need over 70,000 years to reach Proxima Centauri, and it isn't even headed in that direction. This staggering gulf illustrates one of the most profound truths about the universe. Stars may appear clustered in the night sky, but they are separated by oceans of emptiness so vast that they defy ordinary comprehension. Yet Proxima Centauri is more than a lonely beacon in the dark. It is a small but intriguing star with characteristics radically different from our Sun, only about 14% as wide as the Sun, and possessing just 12% of its mass. Proxima burns so slowly and efficiently that it will continue shining for trillions of years, far longer than our Sun's total lifespan. No red dwarf star has ever died of old age. The universe is simply not old enough yet. However, Proxima's modest size comes with volatility. It is a flare star, prone to sudden eruptions of energy that can briefly increase its brightness and bombard nearby worlds with radiation. Such flares complicate the prospects for life on planets orbiting close enough to be warm, and yet, Proxima hosts at least 2 known planets, one of which, Proxima b, lies within the star's so-called habitable zone, where temperatures might allow liquid water to exist. Whether this world is actually capable of supporting life is deeply uncertain. The same radiation bursts that illuminate its surface might also strip away its atmosphere. Still, the presence of planets around the nearest star offers a tantalizing hint that the galaxy may be rich with worlds. Proxima is gravitationally bound to two brighter stars, Alpha Centauri A and Alpha Centauri B, which orbit each other as a binary pair. These two sun-like stars, one slightly larger and one slightly smaller than our own, form a system long considered a prime target for future interstellar probes. From Earth's vantage point, they shimmer together in the southern sky, offering a reminder that even the stars nearest to us come in a variety of configurations. Beyond Alpha Centauri lies Barnard's star, a fast-moving red dwarf about 6 light-years away, aging and dim but among the closest solitary stars. Farther still is Sirius, the brightest star visible from Earth's night sky, located about 8.6 light-years away. Its brilliance in our sky is due not to its proximity alone, but to its intrinsic luminosity. It shines more than 20 times brighter than the Sun. Even so, Sirius is still firmly within our local cosmic neighbourhood. As we progress outward, the scale stretches exponentially. Consider Betelgeuse, a red supergiant in the constellation Orion, roughly 700 light-years away. Its light began travelling toward Earth around the time medieval Europe was witnessing the end of the Crusades. Betelgeuse is so enormous that if placed where our Sun is, its bloated surface would reach past the orbit of Mars. And yet, even this monstrous star is just one of the many thousands dotting our region of the Milky Way. The further we zoom out, the more Earth shrinks, not only physically but conceptually. From Proxima Centauri's vantage point, Earth would not be visible at all. Even with a powerful telescope, our planet would be lost in the Sun's glare, reduced to an undetectable speck, orbiting a pale star among hundreds of billions. In this realm of interstellar distances, Earth ceases to register as anything meaningful. The solar system becomes a tiny spark suspended in a vast, quiet void. And this void is merely the space between stars, a small and relatively calm portion of our home galaxy. As we continue outward toward the Milky Way itself, the scale of our journey will increase not by miles or even trillions of miles, but by light-years numbered in the tens of thousands. Only then will we begin to fully grasp just how minuscule our world truly is against the architectural landscape of the galaxy. Moving farther from the immediate neighbourhood of our Sun and its closest stellar companions, we begin to see that the stars visible from Earth with the naked eye are only a minute sampling of the Milky Way, a galaxy so vast and intricate that even attempting to visualize its full scale forces the imagination to stretch far beyond its familiar limits. The Milky Way contains somewhere between 100 billion and 400 billion stars, each with its own gravitational domain, its own history, and in many cases its own planetary system. When viewed from the side, our galaxy reveals a thin, luminous disk roughly 100,000 light-years across, and only a few thousand light-years thick, like a cosmic blade floating in the darkness. From above, it resembles a majestic spiral with long, curving arms filled with bright newborn stars, glowing clouds of gas, and lanes of interstellar dust. Our Sun resides in a relatively quiet region known as the Orion Spur, a modest offshoot between two of the galaxy's major arms, the Sagittarius and Perseus arms. Positioned about 26,000 light-years from the galactic centre, our solar system circles the Milky Way at a remarkable speed, completing a full orbit once every 225 million years. This means that throughout Earth's entire history, from its molten beginnings to the rise and fall of dinosaurs to the emergence of human civilization, our planet has completed only about 20 revolutions around the galaxy. The last time Earth occupied its current position in the Milky Way, dinosaurs were just starting to establish themselves, and mammals were tiny, timid creatures hiding in the shadows. The enormity of this timescale challenges our sense of duration, revealing that the flow of cosmic time moves at a pace utterly different from our brief human experience. The central region of the Milky Way is a dense, energetic bulge filled with old stars packed far more closely than those in our region of the galaxy. If we lived near the core, the night sky would be ablaze with starlight so intense that darkness would never fully descend. But dust clouds between us and the centre obscure much of this view in visible light, leaving astronomers dependent on infrared and radio observations to peer into the galactic heart. There, Hidden behind these vast curtains of dust lies Sagittarius A, the supermassive black hole that anchors the Milky Way. With a mass equivalent to about 4 million suns, this gravitational titan exerts a powerful influence on its surroundings, shaping the motions of stars that whip around it at extraordinary speeds. One such star, known as S2, completes its highly elongated orbit in just 16 years, racing through space at nearly 5% the speed of light when closest to the black hole, an incredible testament to the immense forces at work in the galactic core. Though Sagittarius A is currently relatively quiet, astronomers have found evidence that it was once more active, unleashing colossal outbursts that left behind massive bubbles of high-energy radiation extending above and below the galaxy's disk. While the central region is bustling with activity, the spiral arms farther out are the birthplace of new stars. Giant molecular clouds collapse under their own gravity, igniting nuclear fusion and producing clusters of hot blue stars that illuminate the surrounding gas. These young stars burn brightly but briefly, living fast and dying in spectacular supernova explosions. Meanwhile, older stars like the Sun drift between the arms, inhabiting calmer regions where star formation has slowed. Encircling the bright disk is the galactic halo, a nearly spherical expanse populated with ancient stars and globular clusters, dense collections of hundreds of thousands of stars bound tightly by gravity. These clusters, such as the famous M13, are among the oldest surviving structures in the galaxy, fossils from a time when the Milky Way was still forming. The halo also contains vast quantities of dark matter, an invisible, enigmatic substance that does not emit or absorb light, but exerts gravitational effects strong enough to shape the galaxy's rotation. In fact, most of the Milky Way's mass is dark matter, extending in a massive halo far beyond the visible disk. Even with all these layers and components, the true extent of our galaxy emerges only when we consider the communities of smaller galaxies orbiting it. Dozens of dwarf galaxies accompany the Milky Way like quiet companions, each with only a few million stars compared to our hundreds of billions. The large and small Magellanic Clouds, visible from the southern hemisphere, are among the most prominent of these satellites, slowly being pulled apart by our galaxy's gravity. Andromeda, our nearest large galactic neighbour, is on a slow-motion collision course with the Milky Way, destined to merge with us in about 4.5 billion years. All of this paints a portrait of a galaxy teeming with structure and complexity, yet our solar system occupies only a tiny, nondescript corner of it, a faint speck among hundreds of billions. At this scale, Earth no longer registers even as a dot. The entire solar system, vast as it once seemed, becomes nothing more than a barely perceptible glimmer within a single spiral arm of a galaxy whose true breadth and richness we are only beginning to understand. At the very centre of the Milky Way, far beyond the quiet suburb where our Sun drifts through its leisurely orbit, lies a region so dense, turbulent, and exotic that it feels like an entirely different universe from the calm star fields we see in our night sky. This central arena, shrouded in thick veils of dust that block visible light, pulses with the energy of millions of stars packed into a volume far smaller than the space between our Sun and its nearest neighbours. Here, gravity reigns with uncompromising authority, sculpting the motions of stars and gas clouds into dizzying orbits that defy our earth-bound intuitions. At the heart of this celestial hive stands Sagittarius A, the Milky Way's supermassive black hole, whose presence is betrayed not by light black holes, emit none but by the frenzied behaviour of the stars that race around it. Although its diameter is only a fraction of that of the Sun, Sagittarius A contains the mass of roughly 4 million suns, collapsed into a region so compact that the surrounding spacetime curves sharply inward. The strongest evidence for this behemoth comes from stars like S2, which dive perilously close to the black hole every 16 years, accelerating to nearly 30 million miles per hour, about 5% of the speed of light, before slingshotting back into space. These stellar whiplashes, observed over decades by powerful telescopes, offer the clearest window we have into the extreme physics governing the galactic core. While Sagittarius A appears relatively dormant today, emitting only faint flickers of radiation as it occasionally consumes bits of gas or dust, astronomers have uncovered vast structures extending above and below the galactic plane colossal bubbles of high-energy particles likely produced by past eruptions from the black hole or explosive star formation episodes in the central region. Such outbursts would have illuminated the galaxy with enormous jets of energy millions of years ago, evidence of a dynamic history now preserved like a cosmic scar. Surrounding the central black hole is the galactic bulge, a thick spheroidal concentration of ancient stars whose ages often exceed 10 billion years. These stars formed early in the Milky Way's history, long before the Sun was born, making them relics from a time when the galaxy was still assembling itself from smaller protogalactic fragments. In the bulge, stars orbit in chaotic, crisscrossing paths rather than the orderly circular motions typical of the galactic disk. If one could stand on a planet near the bulge, the night sky would blaze with thousands of bright stars packed so densely that true darkness might never fall. The constellations familiar to us would dissolve into a brilliant, shimmering tapestry. Radiating outward from the bulge, the Milky Way's spiral arms wind gracefully through the disk, where dense clouds of gas collapse under gravity to ignite new stars. These regions, lit by young, massive blue stars and glowing nebulae, are cradles of cosmic birth. Yet they are also dangerous. The same massive stars that shine fiercely for a few million years end their lives in supernova explosions that can sterilize nearby systems. Our Sun, being older and less massive, drifts between these arms in a calmer neighbourhood, a fortunate position for the evolution of complex life. Beyond the disk and bulge lies the galactic halo, a roughly spherical region populated by sparse, ancient stars and globular clusters. These clusters, some containing hundreds of thousands of stars, orbit the Milky Way like distant companions, their tightly bound, stellar populations glowing as faint but enduring lanterns in the darkness. The halo also houses the mysterious dark matter halo that envelopes the galaxy, a vast reservoir of invisible mass that outweighs the visible stars and gas by a significant margin. Although dark matter cannot be seen or directly detected, its gravitational influence is unmistakable. It prevents the galaxy from flying apart by keeping stars in the outer regions moving faster than they otherwise should. Then there are the Milky Way's satellite galaxies, small, gravitationally bound companions slowly spiraling toward eventual assimilation. The large and small Magellanic Clouds are the most prominent of these, visible as bright smudges in the night sky of the southern hemisphere. Streams of stars torn from these satellites weave through the halo, silent testimonies to the ongoing cannibalistic growth of our galaxy. Others, such as the Sagittarius dwarf galaxy, are in the process of being shredded and absorbed, their stars scattered like cosmic fossils. Meanwhile, far across intergalactic space, the Andromeda Galaxy, our closest galactic cousin, more massive and equally majestic, is inching toward us. In roughly 4.5 billion years, the two galaxies will collide in a slow-motion gravitational dance that will last billions of years, ultimately merging into a single colossal, elliptical galaxy. Despite the word collision, actual star-on-star impacts will be virtually non-existent. Galaxies are mostly empty space. Instead, gravity will reshape their structures, fling stars into new orbits, trigger waves of star formation, and transform the Milky Way into something entirely new. Across all these structures, the bulge, the disk, the halo, the satellites, our solar system is merely one faint, insignificant dot, drifting quietly around the galactic centre on a path so vast that humans have witnessed only a fraction of a single galactic year. At this scale, Earth vanishes entirely, too small to register against the backdrop of hundreds of billions of stars woven into a cosmic city whose size defies imagination. Leaving the Milky Way's internal structure behind, we step into the next level of cosmic architecture, the realm of galaxy groups, where the Milky Way is no longer an isolated island of stars but one member of a modest gravitational community known as the local group. Spanning roughly 10 million light-years, the local group contains more than 50 galaxies, most of them dwarfs so faint and diffuse that they remain invisible to the naked eye even from relatively close distances. The three dominant members are the Milky Way, the Triangulum Galaxy, M33, and the Andromeda Galaxy, M31, which is both the largest and most massive of the ensemble. Andromeda's vast disk stretches more than 220,000 light-years more, than twice the width of the Milky Way, and houses a trillion stars, giving it a gravitational pull strong enough to influence the motions of many smaller galaxies orbiting nearby. Andromeda is not merely a distant neighbour, it is on an inevitable collision course with the Milky Way, racing toward us at about 250,000 miles per hour. Although this speed seems staggering, the distance between the galaxies is so immense, about 2.5 million light-years, that the merger will not occur for another 4.5 billion years. When the two galaxies finally meet, they will not smash together like solid objects. Instead, they will pass through each other repeatedly over billions of years, their stars sailing through the vast expanses of space without colliding. Gravity will distort their shapes, stretch their spiral arms into long tidal tails, and trigger waves of star formation as gas clouds crash together. Ultimately, the two galaxies will blend into a single massive elliptical galaxy, sometimes dubbed Milkdromeda. Yet even before this grand cosmic event unfolds, the local group tells a story of hierarchical structure. Surrounding the major galaxies are numerous dwarf galaxies, some irregular, some spheroidal, whose stars are far fewer and more weakly bound. The large and small Magellanic Clouds, visible from the southern hemisphere, are among the brightest of these companions. They orbit the Milky Way as part of a loose gravitational dance, leaving behind long streams of stars torn from their outskirts by the Milky Way's relentless tidal pull. These stellar streams, faint but measurable, serve as living evidence of the cannibalistic nature of galaxy evolution, a process in which large galaxies grow by absorbing their smaller neighbours. The Triangulum galaxy, though much smaller than Andromeda and somewhat larger than many dwarfs, is still substantial, containing around 40 billion stars spread through a delicate spiral structure. It too is gravitationally bound to Andromeda and plays a role in shaping the dynamics of the local group. But the local group itself is only a small fragment of an even grander structure, the Virgo supercluster. Stretching across at least 110 million light-years, this supercluster contains scores of galaxy clusters and loose groups, collectively housing hundreds of trillions of stars. The Milky Way and its companions occupy a minor, almost peripheral region within this colossal formation. The Virgo supercluster's central feature is the Virgo cluster, a dense congregation of more than 1,000 galaxies located about 54 million light-years from Earth. This cluster includes enormous elliptical galaxies such as M87, a gravitational giant containing roughly 1 trillion stars. At its centre lies one of the most massive black holes ever directly imaged, its event horizon spanning nearly 25 billion miles. M87's central black hole is so massive, around 6.5 billion solar masses, that its gravitational influence shapes the structure and behaviour of the galaxy on enormous scales, launching jets of energetic particles that extend thousands of light-years into intergalactic space. As awe-inspiring as the Virgo supercluster is, it is not an isolated structure either. In 2014, astronomers discovered that the Virgo supercluster is merely one lobe of an even larger gravitational megastructure called Laniakea, which encompasses around 100,000 galaxies spread across a mind-bending 520 million light-years. Laniakea, a Hawaiian word meaning immeasurable heavens, reflects both the cultural reverence for the sky and the near impossibility of grasping such scale. The Milky Way, instead of drifting independently, is being drawn along a vast cosmic flow toward a mysterious region known as the Great Attractor, a gravitational anomaly located about 250 million light-years away. Although partially obscured by the Milky Way's dust and gas, the Great Attractor influences the motions of thousands of galaxies, pulling them toward a region dominated by several massive clusters, including the Norma cluster. But even the Great Attractor is not the final word in cosmic gravitation. Beyond it lies the Shapley supercluster, one of the most massive structures in the nearby universe, whose overwhelming gravitational pull appears to be tugging on Laniakea itself. These layers of structure from the Milky Way to the local group, to the Virgo supercluster to Laniakea, reveal a universe woven together by gravity into an intricate hierarchy. And through all of this, Earth's significance continues to diminish. Compared to the countless galaxies swirling within Laniakea, our planet becomes so small, so unmeasurable, that it effectively disappears. The local group alone contains billions of stars more massive, more brilliant and more exotic than our Sun, Yet even this densely populated neighbourhood is but 1 minute thread in a cosmic tapestry stretching across hundreds of millions of light years. As we trace the vast gravitational currents that sweep entire galaxies across hundreds of millions of light years, we find ourselves compelled to confront a truth even more staggering than the immensity of superclusters. Beyond the enormous web-like structures that bind galaxies together lies a still deeper void, an emptiness so profound that even the largest cosmic formations seem to float like islands in an infinite black sea. The cosmic web, with all its filaments and clusters, is not a dense three-dimensional lattice but a delicate framework stretched across a universe where true substance is extraordinarily rare. Galaxies gather along invisible strands shaped by gravity and dark matter, forming clusters and superclusters, yet between these strands exist vast regions of almost nothing at all. Enormous cosmological voids spanning tens, hundreds, or even billions of light years, where only a handful of galaxies drift in isolation. One of the largest of these empty realms is the KBC void, a region nearly 2 billion light-years across in which the density of galaxies is significantly lower than in surrounding space. If one could stand at the centre of such a void and look outward, the universe would appear noticeably emptier, the familiar tapestry of light flattened into distant sheets and knots far beyond reach. And yet, these vast voids are an essential part of the cosmic architecture. They were sculpted in the universe's infancy, when tiny fluctuations in density mere quantum variations, stretched by the rapid expansion known as inflation, seeded the large-scale structure we see today. Regions slightly denser than average condensed into galaxies and clusters, while slightly emptier regions became ever more evacuated as matter flowed outward under gravity's pull. Over billions of years, these small differences grew into immense contrasts, carving the cosmic web into its present form. Among its most impressive structures is the Sloan Great Wall, a mind-bending assemblage of galaxies stretching roughly 1.37 billion light-years across. Even this is overshadowed by the Hercules Corona Borealis Great Wall, perhaps the largest known structure in the observable universe, spanning an estimated 10 billion light-years, so vast that it challenges the assumptions underlying modern cosmology. According to widely accepted theories, structures of that size should not have had sufficient time to form since the Big Bang, which suggests either that our models remain incomplete or that these colossal walls are loosely connected conglomerations rather than true unified structures. Still, their existence underscores the scale we are now dealing with, a scale in which superclusters and galaxy walls become the basic landmarks of the cosmos. Yet even these tremendous expanses pale when set against the boundaries of the observable universe itself. Though the universe is 13.8 billion years old, the farthest objects we can see are not 13.8 billion light-years away, but closer to 46.5 billion light-years in any direction. This is because space itself has been expanding since the light left these distant galaxies, meaning the observable universe now forms a vast sphere roughly 93 billion light-years across. Within this sphere lie an estimated 2 trillion galaxies, each containing billions or trillions of stars. The total number of stars in the observable universe is on the order of 200 billion trillion, a quantity so vast that if each star were replaced by a grain of sand, the total would fill multiple Olympic swimming pools to the brim. But even this nearly incomprehensible number represents only the visible component. Many galaxies lie beyond our observational reach because their light has not yet had time to reach us. The true universe may be dozens, thousands, or infinitely many times larger than the observable portion. Some cosmological models propose that we inhabit one bubble-like domain in a cosmic foam of countless universes, each born from its own moment of inflation, each with its own physical properties. In such a scenario, everything we call the universe would be only a small patch of a far grander reality, one in which Earth, the solar system, and even the Milky Way would be so inconceivably tiny as to be meaningless. Yet even without invoking a multiverse, the observable universe alone is enough to erase Earth from any quantitative metric. Earth is not merely small, it is not even a detectable feature on cosmic scales. Our entire solar system, vast as it once seemed, is far smaller than a single pixel if the Milky Way were compressed into a digital image. The Milky Way itself becomes a microscopic speck in the Virgo supercluster. That supercluster becomes a faint dot in Laniakea. Laniakea dissolves into one tiny node in the cosmic web. and the cosmic web disappears entirely into the 93 billion light-year expanse of the observable universe. At this stage of our journey, the notion of distance begins to lose meaning. Light years, once useful, become so enormous that they fail to convey true scale. We're dealing now with expanses so immense that they dwarf every structure we have ever known, and within this vastness, within this ancient, silent, expanding sphere of galaxies and voids, floats a single small blue world, orbiting a modest star in an unremarkable corner of an ordinary galaxy. The contrast is overwhelming, yet it is precisely within this staggering asymmetry between scale and significance that humanity's story acquires its extraordinary texture. As we contemplate this universe of staggering scale, its vast walls of galaxies, its almost perfectly empty voids, its trillions of suns scattered across tens of billions of light years, something essential shifts in our perspective. Earth, once the stage upon which all of human history unfolded, now becomes so small that it virtually disappears. And yet, even in the face of this overwhelming vastness, we find ourselves compelled to ask a deeply human question. If the universe is so large, and if stars and planets are so numerous, should life not be common? This simple question lies at the heart of one of the most enduring puzzles in modern science, the Fermi paradox. Put simply, the paradox observes that the universe is old enough, large enough, and rich enough in potentially habitable worlds that technologically advanced civilizations should have emerged long before ours and spread throughout the galaxy. Even travelling at a fraction of the speed of a light, a civilization with millions of years at its disposal could, in theory, explore or colonize the Milky Way many times over. And yet, despite decades of searching, we find no definitive evidence of alien life. No radio signals, no artificial structures, no cosmic engineering projects, no unmistakable traces of intelligence. Enrico Fermi phrased this contradiction in 4 famous words. Where is everybody? One possible answer is stark. Intelligent life may be incredibly rare. While microbial or simple organisms might arise wherever conditions allow, the leap from single-celled life to complex multicellular organisms may be extraordinarily unlikely. On Earth, life appeared relatively quickly, within a few 100 million years of the planet becoming habitable. But then, for nearly 3 billion years, nothing more advanced than bacteria populated the planet. Complex life emerged only after a sequence of improbable evolutionary events, culminating in intelligent beings capable of technology. Perhaps most planets never make this leap. Another possibility is that intelligent civilizations tend to self-destruct before reaching the stage where they can explore the galaxy. Technological species might face existential challenges: war, environmental collapse, uncontrolled artificial intelligence, or other unforeseen hazards that prevent them from surviving long enough to master interstellar travel. If civilizations routinely destroy themselves shortly after developing advanced technology, then the galaxy might be littered with countless worlds that briefly produced intelligence only to fall silent before they could communicate or expand. There is also the idea that intelligent life is common but cautious. Perhaps advanced civilizations deliberately avoid broadcasting their presence, either out of fear, ethical restraint, or a general principle of non-interference. Some might operate in ways that leave no detectable signature or use communication methods beyond our current understanding. Even if they wish to contact us, they might judge humanity too primitive, too volatile, or too short-lived to merit engagement. Another explanation lies in the sheer breadth of cosmic time and the incomprehensible distances between stars. Even if civilizations flourish, they might be separated by millions of years or tens of thousands of light years, too far apart for any meaningful interaction. Signals degrade, civilizations rise and fall, and stars drift across the galaxy over billions of years. It is entirely possible that advanced species existed long before humanity evolved and disappeared long before we looked to the sky. Or they may arise long after we are gone. In this view, the silence we observe is not a sign of absence, but the loneliness inherent in a universe where even the most advanced beings are isolated by time and distance. Still, despite these sobering possibilities, Earth remains the only confirmed cradle of life. We may discover microbial fossils on Mars, chemical traces in the clouds of Venus, or signs of life in the subsurface oceans of Europa or Enceladus. We may one day find atmospheric biomarkers on distant exoplanets, or decipher signals from faraway stars. But as of this moment, we stand alone, and that uniqueness lends our planet extraordinary value. If intelligent life is exceedingly rare or fleeting, then Earth represents something profoundly special, a world where matter has temporarily organized itself into beings capable of reflection, creativity, and awareness. This perspective transforms the question of alien life from mere speculation into an existential responsibility. If humanity is alone, then the survival of conscious thought becomes our burden to carry, a burden measured not merely on planetary or historical scales, but on cosmic ones. Yet this loneliness also carries a strange beauty. It hints that intelligence, far from being a trivial outcome of cosmic evolution, may be one of the rarest and most precious phenomena in existence. All the distant galaxies, blazing with hundreds of billions of stars, might be utterly silent, devoid of minds to witness their brilliance. If so, the existence of even one intelligent species transforms the universe from a vast unconscious mechanism into something alive with meaning. And that species, improbably, resides on a small rocky planet orbiting an ordinary star in an unremarkable corner of the Milky Way, a planet whose significance does not come from size or location, but from the fragile spark of thought it sustains. To understand just how improbable our existence is, we must examine not only the vastness of space, but also the structure of matter itself, because Earth's insignificance is not merely a matter of size compared to galaxies. It is also rooted in the invisible scales that make up the physical world around us. Everything on Earth, from mountains to oceans to living creatures, is composed of atoms, tiny structures so small that tens of millions of them could line up across the width of a single human hair. An atom is mostly empty space, with a dense nucleus composed of protons and neutrons surrounded by a cloud of electrons occupying a region thousands of times larger than the nucleus itself. If an atom were the size of a football stadium, the nucleus would be a grain of sand at the center, while the electrons would swarm around near the outer walls. The entire stadium would be empty. This emptiness pervades all matter: your body, the air around you, the ground beneath your feet, and even the stars themselves. Although matter feels solid, that solidity arises from electromagnetic forces that prevent atoms from passing through each other, not from atoms touching in any literal sense. This means that Earth, despite its mass of roughly 6 trillion kilograms, is composed almost entirely of empty space, arranged in a delicate lattice of particles. If you stripped away all the empty space and compressed the entire planet to the density of an atomic nucleus, Earth would shrink from its nearly 8,000-mile diameter to a sphere less than 1,000 feet wide, small enough to fit comfortably within a city block. Yet even this shriveled version of Earth would still contain all its mass, demonstrating just how misleading our sense of physical scale can be. Digging deeper into the atom, we find that protons and neutrons are themselves composed of even smaller entities called quarks, bound together by gluons in a dance governed by the strong nuclear force. Quarks and electrons appear to be fundamental, with no internal structure as far as experiments have revealed. Below them lie quantum fields, mathematical constructs that permeate all of space and give rise to particles through fluctuations. In this view, matter is not a collection of tiny solid objects, but a set of excitations within invisible fields. The universe at its most basic level is a restless sea of energy, out of which particles and therefore planets, stars and people emerge like temporary ripples. Stepping upward again in scale, atoms combine to form molecules, which assemble into minerals, water, air, and organic compounds. These form cells, tissues, ecosystems, and eventually conscious beings capable of contemplating their own composition. The number of atoms in the human body alone is staggering around 7 octillion, a 7 followed by 27 zeros, all coordinated to sustain life for only a brief moment in cosmic time. Earth itself contains something like 10 to the 50 atoms, a number so vast that if you attempted to count them at 1 atom per second, you would need more than 10 trillion times the current age of the universe to finish. Yet despite this unimaginable abundance of atoms, the planet they constitute is still nothing more than a microscopic fleck in the solar system, which is a microscopic fleck in the galaxy, which is an invisible whisper in the larger universe. The scales stack endlessly, from quarks to protons to atoms to molecules to mountains to planets to stars, to galaxies, to the cosmic web, and at every level, Earth remains insignificant in size. Even time conspires to shrink our sense of importance. Earth formed about 454 billion years ago, and for most of that time it was devoid of complex life. Microbial life appeared relatively early, about 3.8 billion years ago, but multicellular organisms did not emerge until roughly 600 million years ago, and the human lineage only within the last few million years. Modern Homo sapiens arose a mere 300,000 years ago, less than 1/10 of 1% of Earth's history. The entire span of recorded human civilization fits within the last 6,000 years, a blink of cosmic time. If Earth's history were compressed into a single calendar year, humans would appear only in the final 30 minutes of December 31st, and everything we consider history would occupy the last few seconds before midnight. Meanwhile, the universe itself stretches back 13.8 billion years, more than 3 times Earth's age, and will likely continue for trillions of years to come. Our species occupies not just a vanishingly small region of space, but a vanishingly brief moment in time. When we combine both perspectives, the microcosm of atomic structure and the macrocosm of cosmic evolution, we see Earth in its true context, a temporary concentration of matter within an unfathomably vast and ancient universe. Yet it is precisely this combination that makes our world remarkable. Out of empty space and elementary particles arranged through forces we barely understand, emerged a planet capable of supporting life. Out of that life emerged consciousness, and out of consciousness emerged curiosity, the ability to ask what the universe is made of, how it came to be, and what our place within it might mean. For all its smallness, Earth has become a vantage point from which the universe reflects upon itself, and that makes this tiny world far more than the sum of the atoms that compose it. To follow Earth's diminishing presence against the backdrop of ever-expanding cosmic structures, we now return to one of the most extraordinary features of our own galaxy, the supermassive black hole at its centre. This enigmatic object, Sagittarius A, anchors the Milky Way with a gravitational force so immense that stars whip around it in dizzying high-velocity orbits, tracing paths that reveal its invisible mass. Although smaller in diameter than many stars, Sagittarius A packs the mass of about 4 million suns into a region so compact that space-time itself folds inward, creating an event horizon from which nothing, not even light, can escape. Astronomers deduced its presence by observing stars such as S2, which curve around the black hole in astonishingly tight orbits, accelerating to a few percent of the speed of light. At closest approach, S2 plunges within a distance comparable to the span between the Sun and Saturn, completing each orbit in a mere 16 years, a breathtaking demonstration of gravitational extremes. Yet Sagittarius A is comparatively quiet today, consuming only small amounts of infalling gas and dust, emitting faint flares detectable in infrared and radio wavelengths. But evidence suggests this calm is not permanent. Astronomers have identified enormous lobes of high-energy particles, so-called Fermi bubbles, ballooning tens of thousands of light-years above and below the galactic disk. These structures likely formed from a dramatic outburst millions of years ago, either from a surge of matter plunging into the black hole, or from a burst of star formation near the galactic centre. These colossal scars hint at a more volatile past, reminding us that even dormant black holes can awaken with galaxy-shaping consequences. Surrounding Sagittarius A is the galactic bulge, a swollen sphere of ancient, densely packed stars. Many of these stars are more than 10 billion years old, relics from the earliest stages of the Milky Way's formation. Their orbits are chaotic rather than orderly, swirling in all directions like a cosmic beehive. If one could hover inside the bulge, the night sky would be ablaze with starlight, far brighter than anything visible from Earth. Dust lanes obscure much of this region from optical view, but infrared telescopes pierce the shroud, revealing the crowded stellar metropolis beneath. Beyond the bulge stretches the galactic disk, where stars, gas, dust, and nebulae organize themselves into sweeping spiral arms. These arms are not rigid structures but density waves regions where interstellar material is compressed, triggering new waves of star formation. Hot, massive stars illuminate their birthplaces in brilliant hues, but they burn out quickly, often exploding as supernovae before drifting far from where they formed. The Sun, by contrast, is a middle-aged, stable star that has wandered away from its birthplace and now drifts through a quieter interarm region, a cosmic suburb shielded from the most violent stellar events. Encasing the disk is the galactic halo, a vast, diffuse sphere populated with ancient stars, stellar streams, and globular clusters. These clusters are some of the oldest surviving structures in the galaxy, tightly bound collections of hundreds of thousands of stars orbiting together like swarms of luminous bees. They are fossils from the Milky Way's early evolution, offering clues about the galaxy's origins and its interactions with smaller satellite galaxies. Orbiting within this halo are dozens of dwarf galaxies, tiny, ghostly assemblages of stars held loosely by the Milky Way's gravity. Many bear the marks of tidal disruption, their stars stretched into long, meandering streams that wrap around the galaxy like faint glowing ribbons. These stellar streams reveal the Milky Way's ongoing cannibalism. Over billions of years, it has absorbed countless smaller galaxies, each merging event leaving behind a subtle trace. Beneath all of this visible structure lies something even more mysterious: the galaxy's dark matter halo. Although invisible and undetectable by conventional means, dark matter makes up most of the Milky Way's mass. Its gravitational influence keeps the galaxy rotating more quickly than it should based on visible matter alone. Without this hidden scaffolding, the Milky Way would fly apart, unable to hold its stars together. Dark matter extends far beyond the luminous disk, forming a giant spherical cushion that encompasses the galaxy and its satellites. Yet even with its vast mass and intricate architecture, the Milky Way is only one of trillions of galaxies in the observable universe, each with its own black hole, spiral arms, halo, and history of mergers. And within this cosmic ecosystem, Earth does not even register as a meaningful component, not a pixel, not a speck, not a measurable point. If the entire Milky Way were reduced to the size of a grain of sand, Earth would shrink to something smaller than a proton, utterly beyond the reach of visualization. It becomes clear then that on galactic scales, Earth truly disappears, not metaphorically, but quantitatively. Yet paradoxically, from this vanishingly small world emerges the only known beings capable of studying galaxies, uncovering the behaviors of black holes, and pondering the nature of dark matter. The more insignificant Earth becomes in size, the more extraordinary its role becomes in understanding the universe. As we continue drifting outward from the Milky Way, the next level of cosmic structure emerges: the local group, a gravitationally bound family of galaxies spanning roughly 10 million light-years and containing over 50 members, most of them small, faint dwarf systems that barely glow against the darkness. At its heart are three major spirals: the Milky Way, the Triangulum Galaxy, M33, and the dominant giant of the group, the Andromeda Galaxy, M31. Andromeda is a majestic spiral more than 220,000 light-years across, home to 1 trillion stars, vast star-forming regions, and a supermassive black hole several times the mass of Sagittarius A. Although it now lies about 2.5 million light-years from us, it is approaching at roughly 250,000 miles per hour, pulled by the combined gravitational tug between our galaxies. This seemingly impossible speed is dwarfed by the scale of distance involved. Even at such velocity, Andromeda will not collide with the Milky Way for another 4.5 billion years, and when the collision does occur, it will unfold not as a catastrophic crash, but as a slow gravitational ballet lasting billions of years. The vast emptiness inside galaxies ensures that almost no stars will physically collide. Instead, the two islands of stars will pass through one another, their shapes stretched and distorted by tidal forces, their gas clouds compressed into new star-forming bursts, and their stellar populations mixed, until the two spirals ultimately merge into a single, enormous elliptical galaxy, an entity astronomers whimsically nickname Milkdromeda. Yet the local group is more than just these major players. The Milky Way, like a cosmic monarch surrounded by a retinue of smaller companions, hosts dozens of dwarf galaxies that orbit within its gravitational domain. Some, like the Sagittarius dwarf galaxy, are in the process of being torn apart, their stars strewn across the halo in long, fragile streams. Others, such as the Fornax and Sculptor dwarves, quietly orbit at great distances, containing only a few million stars each. The large and small Magellanic Clouds. The most visible satellites are irregular dynamic galaxies with their own star-forming regions and complex gravitational interactions. These luminous clouds are slowly being drawn toward the Milky Way, leaving behind trails of gas and stars that map their winding orbits. Their presence in Earth's southern skies has guided navigators for centuries and now provides astronomers with invaluable insight into the evolution of satellite galaxies. Further out lies Triangulum, the local group's third largest galaxy, a delicate spiral with around 40 billion stars. Though far smaller than Andromeda or the Milky Way, Triangulum is gravitationally bound to them and may eventually participate in the grand merger billions of years from now. But even this three-galaxy hierarchy is just a tiny part of something vastly larger, the Virgo supercluster, an enormous collection of galaxy clusters and groups stretching around 110 million light-years. The local group occupies only one small corner of this monumental structure, much like a neighbourhood tucked away within a sprawling megacity. The supercluster's core is dominated by the Virgo cluster, a massive congregation of more than 1,000 galaxies located about 54 million light-years from Earth. Among these galaxies are enormous elliptical titans like M87, whose central black hole imaged in 2019 by the Event Horizon Telescope is among the most massive ever observed, weighing billions of times the mass of the Sun. This gravitational monster drives colossal jets of superheated plasma, extending tens of thousands of light-years into intergalactic space. The Virgo cluster is not a peaceful place. Galaxies there are constantly interacting, colliding, and being stripped of their gas by hot intracluster plasma. Star formation is triggered or quenched depending on these interactions, giving the cluster a vibrant and chaotic dynamism. But the true revelation came when astronomers discovered that the Virgo supercluster itself is only one part of an even larger cosmic entity called Laniakea, a gargantuan supercluster spanning some 520 million light-years and containing about 100,000 galaxies. The name, derived from Hawaiian and meaning immense heavens, captures both the awe and the incomprehensibility of its scale. The Milky Way is not drifting randomly through space, but is being pulled along vast gravitational channels toward a region known as the Great Attractor, a mysterious concentration of mass obscured by the dust of the Milky Way's plane. Even more remarkably, Laniakea is being influenced by a still larger structure, the Shapley supercluster, one of the densest and most massive galaxy concentrations in the nearby universe. These interconnected flows create a dynamic cosmic landscape where galaxies move like leaves on a vast, slow-moving river of gravity. Within this swirling hierarchy, Earth's status shrinks further. If the local group were a small town in a continental empire, Earth would not even be a grain of dust. It would be a mote floating unnoticed in a sunbeam. Our planet, once the centre of myth and meaning, now resides in a structure so immense that even the Milky Way itself becomes a regional landmark rather than a defining feature. And we have not yet reached the full scale of the universe. As our journey expands beyond the local group and into the vast expanse of the Virgo supercluster, we encounter a realm in which even entire galaxies begin to resemble scattered flecks, suspended in a gravitational tide far more powerful than any individual structure within them. The Virgo supercluster, spanning at least 110 million light-years, is a sprawling assembly of galaxy clusters and smaller groups, each bound together through an intricate interplay of mass and momentum. At its heart lies the Virgo cluster, a colossal congregation of more than 1,000 galaxies dominated by immense elliptical giants. Among these, none is more iconic than Messier 87, a behemoth harbouring a supermassive black hole so enormous, around 6.5 billion times the mass of the Sun, that its event horizon stretches nearly 25 billion miles across. This monstrous black hole, directly imaged by the Event Horizon Telescope in 2019, spews jets of relativistic plasma thousands of light-years into space, illuminating the profound violence that can unfold at the centres of the universe's largest galaxies. The Virgo cluster is not a tranquil environment. Galaxies here plunge through a searing intracluster medium at tremendous speeds, shedding gas, triggering bursts of star formation, or having their star-forming material stripped away entirely. Collisions and mergers are not rare cosmic events, but routine processes, shaping the evolution of the cluster's galaxies over billions of years. Spirals become ellipticals, dwarf galaxies are torn apart and assimilated, and tidal debris forms arcs and streams that lace through the cluster like faint celestial threads. Yet as massive as the Virgo supercluster is, it is only a modest component of something even more extraordinary, the supercluster complex known as Laniakea. Identified in 2014, Laniakea reshaped our understanding of the large-scale structure of the universe. Stretching roughly 520 million light-years in diameter and containing around 100,000 galaxies, Laniakea encompasses not only the Virgo supercluster, but a sweeping network of interconnected galaxy clusters, filaments, and groups all converging toward a central gravitational basin. This structure is so vast that the Milky Way occupies only a tiny peripheral zone, drifting slowly along gravitational currents much like a buoy carried in a slow-moving cosmic river. At the centre of this immense flow lies the region known as the Great Attractor, a gravitational anomaly hidden behind the dense dust of the Milky Way's plane. For decades, astronomers could detect its influence galaxies, including our own, appeared to be moving toward a patch of sky at peculiar velocities that could not be explained by cosmic expansion alone. Yet the cause remained obscured. Gradually, observations across radio, infrared, and X-ray wavelengths revealed that the Great Attractor is not a single object, but a concentration of mass involving several large galaxy clusters, including the massive Norma cluster. Its gravitational pull is so extensive that it shapes the motion of galaxies across hundreds of millions of light-years, pulling entire clusters toward it in a slow and relentless drift. But even this gravitational basin is not the deepest well in our region of the cosmos. Beyond the Great Attractor lies the Shapley supercluster, one of the most massive galaxy concentrations within 1 billion light-years. Containing more than 25 major galaxy clusters and thousands of galaxies in total, Shapley exerts a gravitational influence so profound that it appears to be tugging on Laniakea itself. The combined effects of the Great Attractor and the Shapley supercluster create a complex motion known as the cosmic flow, a coordinated drift of galaxies, including the Milky Way, toward regions of higher mass concentration. These movements occur at hundreds of kilometers per second, yet on human timescales they are imperceptible, a reminder that the universe operates on rhythms far slower and grander than our fleeting lifetimes can observe. Thinking of the universe in this way, structured not as a uniform sea of galaxies but as a dynamic landscape sculpted by vast gravitational currents, shifts our perspective dramatically. We're no longer inhabitants of a single galaxy, but passengers moving along colossal rivers of mass and energy, carried effortlessly through the cosmic web. Earth, once our entire world, becomes a speck inside the Milky Way, which becomes a mote within the local group, which becomes a mere node in the Virgo supercluster, which in turn is just one part of Laniakea, which itself is only one filament among countless others woven into the structure of the observable universe. At these scales, the idea of Earth having any measurable size collapses entirely. Even the Milky Way, with its hundreds of billions of stars, shrinks into insignificance against structures spanning hundreds of millions of light-years. Yet paradoxically, the smaller Earth becomes in this hierarchy, the more staggering it seems that life and conscious life no less arose here at all. A planet that vanishes into nothingness when measured against Laniakea somehow hosts beings capable of mapping Laniakea's shape, detecting the influence of the Great Attractor, and identifying the pull of the Shapley concentration far beyond it. In this sense, Earth's significance is not geometric but intellectual, a tiny platform from which the universe has become aware of its own vastness. As we follow the gravitational pathways that sweep through Laniakea, our understanding of the cosmos undergoes another profound transformation. For these immense structures, superclusters, filaments, and voids are not isolated features, but interconnected components of a larger cosmic flow shaped by the mysterious scaffolding of dark matter and the steady expansion of space itself. Laniakea, enormous as it is only one basin within a vast network of gravitational domains extending across hundreds of millions of light-years, each guiding the motions of galaxies like eddies in a colossal, slow-moving ocean. Our Milky Way, along with the local group and the Virgo supercluster, drifts along one such gravitational river toward the region called the Great Attractor. But pressing further into this continent-sized stretch of cosmic real estate reveals that the Great Attractor is not the final destination of our motion. Instead, it represents a kind of midway convergence, a region where countless galaxies momentarily funnel together on their larger journey toward an even greater mass concentration, the Shapley supercluster. The Shapley concentration, located roughly 650 million light-years away, is one of the most massive galaxy assemblies in our cosmic neighbourhood. With more than 25 major clusters and thousands of galaxies packed into a relatively compact region, it exerts a gravitational influence so immense that it tugs on entire superclusters, including Laniakea. This means that our own galaxy's movement is shaped not just by nearby structures, but by massive formations, unimaginably distant structures that dwarf the Virgo cluster, dwarf Laniakea itself, and hint at a hierarchy of cosmic architecture that continues far beyond anything we have fully mapped. When astronomers look at the motions of galaxies around us, they see a clear pattern. Galaxies are not drifting randomly, but flowing coherently towards Shapley, as though being pulled downhill into an invisible gravitational valley. Even the Great Attractor, once thought to be the primary cause of this motion, appears to be only a waypoint along this plunge toward greater mass. This coordinated motion is known as the bulk flow, and while its existence is well documented, the deeper origins of such massive structures remain mysterious. In many ways, the Shapley supercluster challenges our assumptions about the uniformity of the early universe and raises questions about how such a colossal region of overdensity could have formed in a cosmos still smoothing itself out after the Big Bang. But even Shapley, impressive as it is, resides within something larger still, a cosmic web of filaments and walls connecting superclusters into megastructures spanning billions of light-years. These interconnected filaments stretch across the universe like luminous tendrils, while enormous voids regions with almost no galaxies at all sight between them like vast cosmic deserts. In this grand architecture, Laniakea is merely one filament among innumerable others, each forming part of a network so large that it pushes the limits of human comprehension. On these scales, galaxies behave like dust motes caught in a swirling current, drifting along paths determined by dark matter, the invisible backbone of the universe. Dark matter neither emits nor absorbs light, yet its gravitational imprint is unmistakable, shaping galaxy clusters, bending starlight, and defining the cosmic web structure. Without it, galaxies would not form, superclusters would not cohere, and the universe would be a featureless expanse rather than the intricate tapestry we observe. The interplay between dark matter and dark energy, another mysterious force that drives the accelerating expansion of the universe, determines the fate of all large-scale structures. Dark energy gradually stretches space itself, making distant galaxies recede faster over time. In the far future, gravitationally unbound structures will drift entirely out of view, leaving only the local group gravitationally intact. Even Laniakea, enormous as it is, will not remain a visible collective forever. Its galaxies, presently joined by gravity and motion, will eventually slip away from one another, carried by the expanding fabric of the universe until their light can no longer reach us. The cosmic web will thin, filaments will fade, and isolated island universes will remain, each evolving alone in a universe that becomes colder, quieter, and darker with time. In this sense, the structures we observe today exist during a uniquely transparent moment in cosmic history. We are fortunate to live in a universe still young enough that we can see billions of light years into the distance and map the vast architecture of galaxies, superclusters, and gravitational rivers. Billions of years from now, intelligent beings, if any remain, will see only a tiny portion of what we see today, their observable universe limited to the remnants of their local structures. Against this immense and ever-changing backdrop, Earth becomes vanishingly small, a world orbiting a minor star in a galaxy swept along currents dictated by structures so large that they dwarf even superclusters. And yet from this tiny platform of consciousness, humans have managed to chart the motions of galaxies hundreds of millions of light-years away, infer the presence of unseen matter, and trace the cosmic flows that shape the universe on scales beyond imagination. Earth, for all its smallness, remains the one place where the cosmos has become aware of its own grandeur. As we zoom even farther outward into the cosmic landscape, beyond the reach of individual superclusters, and beyond the gravitational basins that guide galaxies along invisible streams, we begin to see the true tapestry of the universe, the vast cosmic web, a structure so immense and so intricate that it represents one of the most astonishing revelations in modern astronomy. What appears at first glance to be a random scattering of galaxies across the sky is, on larger scales, an organised network of filaments, sheets, walls, and voids created by the interplay of gravity, dark matter, and the initial fluctuations seeded during the earliest moments after the Big Bang. These filaments, the cosmic highways of the universe, contain not just galaxies but clusters of galaxies, hot gas and dark matter woven together into elongated structures stretching hundreds of millions of light-years across. Where multiple filaments intersect, they form nodes, rich clusters and superclusters that anchor the cosmic web like knots in a three-dimensional net. Between these glowing threads, the universe falls away into enormous void stretches of space so empty that entire galaxies are separated by tens or even hundreds of millions of light-years from their nearest neighbours. One of the most striking examples of this architecture is the Sloan Great Wall, a massive collection of galaxies stretching roughly 1.37 billion light-years, discovered through extensive sky surveys mapping the distribution of galaxies across the cosmos. Yet even this colossal formation pales in comparison to the Hercules Corona Borealis Great Wall, an extraordinary structure spanning an estimated 10 billion light-years, nearly a tenth of the observable universe. Its immense scale challenges our understanding of cosmic evolution, because structures that large should not have had enough time to form within the widely accepted models of cosmic expansion. Whether these walls represent true coherent formations or vast coincidental alignments remains a subject of active debate, but their existence underscores the degree to which the universe defies intuition. Alongside these walls lie unimaginable voids like the Bhuta's Void, a staggering region approximately 330 million light-years across containing only a sparse handful of galaxies. If Earth were situated within such a void, the night sky would be shockingly barren. The familiar Milky Way and its millions of stars would be absent, replaced by a lonely, dim universe. The presence of such vast emptiness reveals just how unevenly matter is distributed on cosmic scales. Rather than a smooth, even mixture of galaxies, the cosmos resembles a sponge-like lattice with dense walls and nearly hollow interiors. These patterns originated from minute differences in density, present in the early universe tiny fluctuations of temperature and energy imprinted on the cosmic microwave background radiation. As the universe expanded and cooled, gravity amplified these fluctuations, pulling matter together into filaments while allowing less dense regions to empty out into voids. Over billions of years, this process sculpted the cosmic web we observe today. Yet even the cosmic web is not static. Filaments slowly funnel galaxies toward larger structures, voids expand as their sparse contents drift outward, and clusters merge to form ever larger conglomerates. The cosmic web evolves at a glacial pace, but over billions of years its shape transforms, reflecting the dynamic nature of the universe itself. At this scale of structure, where billion light-year formations outline the skeleton of the cosmos, Earth's insignificance becomes almost surreal. The solar system no longer registers as anything measurable. The Milky Way becomes a minor spark embedded in a long, delicate filament. The Virgo supercluster dissolves into one node among thousands, and Laniakea is reduced to a mere tributary of an incomprehensibly vast cosmic river. Everything humanity has ever known, every thought, discovery, civilization, and life form, resides in a location so tiny within the cosmic web that it disappears into mathematical rounding errors. Even light years, once useful for describing the distance between stars, now collapse under the weight of scales that require billions of light years to describe the spacing between major structures. And yet, while Earth fades from view on cosmic maps, the cosmic web offers a profound perspective on the universe's history and fate. Each filament is a testament to the primordial seeds laid down in the earliest fractions of a second after the Big Bang. Each void records the relentless expansion of space and the tug-of-war between gravity and dark energy. And each cluster, glowing brightly at filament intersections, marks a region where matter has triumphantly overcome the thinning of the universe to build entire galaxies of stars. Despite Earth's infinitesimal size, it is from this tiny world that humans first detected the cosmic microwave background, mapped the distribution of galaxies, measured the accelerating expansion of the universe, and discovered the cosmic web. This fact alone gives Earth a unique significance. It is not large, central, or physically important, yet it is the platform from which the universe's grand structure has been revealed. As we stand at the threshold between the cosmic web and the broader universe beyond, Earth becomes both impossibly small and improbably meaningful, a world so minuscule it dissolves into the background, yet so remarkable that it has produced beings capable of comprehending structures stretching across billions of light years. As we push beyond the filaments and voids that define the cosmic web, we inevitably confront the greatest scale available to human observation, the entire observable universe, a sphere of space centered on Earth, or more accurately on the position of the observer, reaching out roughly 46.5 billion light-years in every direction. This radius is far larger than the universe's age, 13.8 billion years might suggest, because while light was travelling toward us, the fabric of space itself continued to expand, stretching the distance between distant galaxies and our vantage point. The result is a cosmos whose observable diameter spans an astonishing 93 billion light-years. Within this immense volume lie an estimated 2 trillion galaxies, though this number continues to evolve as new data and deeper surveys refine our understanding. Every galaxy contains billions or trillions of stars, and around those stars orbit planets of every conceivable size, temperature, composition, and orbit. The total number of stars, about 200 billion trillion, is so vast that attempting to count them at 1 per second would require more time than the current age of the universe multiplied by millions. And yet these stars represent only a fraction of the matter in the universe. Most of the cosmos is invisible to us, composed of dark matter, which exerts gravitational force and dark energy, the mysterious driver responsible for accelerating the expansion of space. If we look deep enough, we eventually reach the cosmic microwave background, the oldest light in the universe, a faint afterglow left over from the moment when the cosmos cooled enough for atoms to form. This radiation, detectable in every direction, is a snapshot of the universe when it was just 380,000 years old. Its tiny temperature fluctuations, only millionths of a degree, encode the blueprint of all future cosmic structure, mapping the seeds that would grow into galaxies, clusters, superclusters, and the cosmic web itself. But beyond the cosmic microwave background lies something even more elusive. The surface of last scattering marks the boundary of what we can observe. Light from earlier times simply cannot reach us because the universe was opaque before that epoch. Everything earlier belongs not to the observable universe, but to the realm of theoretical physics. The universe may extend far beyond this horizon, possibly infinitely, but we cannot observe, measure, or even meaningfully describe those unseen regions. The 93 billion light-year sphere is merely the bubble of visibility carved out by the speed of light and the passage of cosmic time. Yet even this observable portion is likely just a fraction of a much grander structure. Some cosmological models propose that the universe is flat and infinite, extending forever in all directions. Others suggest that space may curve back on itself like the surface of a sphere, meaning travelling far enough in one direction would eventually return you to your starting point. Still others imagine the universe as a finite but unbounded shape, analogous to a four-dimensional hypersphere. And beyond all these interpretations lies the possibility of the multiverse, the idea that our universe is just one bubble in a vast foam of universes, each with its own physical laws, constants, and configurations. Some could be sterile and empty, others might teem with life, most would be forever inaccessible to us. If the inflationary model of cosmology is correct, then countless pocket universes could be budding off from an ever-expanding background of exponential growth, forming an infinite mosaic of realities. In this context, Earth's scale plummets into irrelevance so extreme it becomes difficult to articulate. Our planet is smaller than a grain of sand compared to the Earth. The Earth is smaller than a grain of sand compared to the solar system. The solar system is a grain of sand compared to the galaxy. The galaxy is a grain of sand compared to the observable universe, and the observable universe itself may be a grain of sand compared to the multiverse. The ladder of scale climbs so quickly that human intuition collapses long before reaching its top. And yet, in spite of this overwhelming smallness, Earth occupies a unique position. It is the only known world where matter has arranged itself into living systems capable of questioning their origins. From a cosmological perspective, consciousness is vastly rarer than atoms or stars, it may be the scarcest and most delicate phenomenon in existence. If intelligent life is truly rare, then the emergence of thinking beings on Earth represents an event of profound cosmic significance. Out of the trillions of galaxies and quintillions of stars, one tiny world has produced minds able to decode cosmic background radiation, measure galactic redshifts, map dark matter, and theorize about other universes beyond our own. The more the universe expands, the more astonishing it becomes that life, fragile and transient though it may be, has appeared at all. And with each discovery, our understanding grows even as Earth's physical relevance shrinks, revealing a universe so vast that our smallness becomes not a source of despair, but a testament to the extraordinary fact that awareness has emerged from the most unlikely of circumstances. As we contemplate the observable universe, its trillions of galaxies, vast webs of structure, and overwhelming stretches of empty darkness, we inevitably return to one of the deepest and most haunting questions humanity has ever asked. Are we alone? Given the sheer immensity of the cosmos, it seems almost inconceivable that life could have arisen only once, on a single rocky world orbiting an ordinary star in a nondescript corner of the Milky Way. And yet, despite decades of searching, Earth remains the only confirmed cradle of life. This tension between statistical expectation and observational silence defines the Fermi paradox. The stubborn mystery of why a universe so rich in planets and so ancient in age has not yet revealed any signs of intelligent life beyond our own. Some scientists argue that life itself may be relatively common simple organisms, forming wherever water, energy and time converge, but that the leap to complex multicellular life is extraordinarily improbable. On Earth, life emerged quickly once conditions stabilized, yet for nearly 3 billion years it remained at the microbial level. Complex organisms appeared only after a series of rare evolutionary breakthroughs, and intelligence, especially technological intelligence, arose only in the last moment of Earth's history. Perhaps then, microbial life pervades the galaxy, while advanced civilizations are exceptions so rare that their existence might be measured in single digits across an entire observable universe. Another possibility is that intelligent life arises more frequently, but rarely survives long enough to become detectable. Civilizations might flourish for a few thousand years, a blink on cosmic scales before succumbing to war, environmental collapse, resource depletion, artificial intelligence gone awry, or challenges we cannot yet imagine. If most civilizations self-destruct shortly after developing advanced technology, then the galaxy could be filled with countless worlds that briefly became aware before falling silent forever. This idea, sometimes called the Great Filter, suggests that we either passed an extraordinarily unlikely threshold in our distant past, or are heading toward a barrier that most civilizations fail to overcome. A third explanation is that intelligent civilizations exist but choose to remain undetected. They may observe strict non-interference, refusing to disrupt the development of younger species. They may camouflage their presence to avoid attracting attention from potential threats. Their communication methods may be so advanced quantum entanglement, exotic particles, multidimensional physics, that we lack the tools or theories needed to recognize their signals, or they may simply have no interest in contacting species as primitive and short-lived as ours. Another solution lies in the immensity of cosmic distances and timescales. Even if life flourishes throughout the galaxy, civilizations could be separated by tens of thousands of light years and millions of years of evolution. By the time one species develops radio technology and sends signals into space, potential recipients may have already perished or may not yet have arisen. Entire civilizations could rise and vanish without ever overlapping in time. The universe's scale does not merely separate us spatially, it isolates us temporally as well. Yet the most sobering possibility is the simplest. Perhaps Earth is genuinely rare. Perhaps the chain of cosmic events that produced life, complex biology, intelligence, and technological capability represents a near impossible sequence of coincidences. Our sun must be stable for billions of years. Our planet must lie in a razor-thin habitable zone. Our moon must stabilize Earth's axial tilt. Plate tectonics must recycle nutrients. Catastrophic impacts must be neither too frequent nor too severe. Evolution must stumble upon sentience. Under this perspective, Earth is not one world among many, but one oasis among deserts stretching for billions of light years. But embedded within all these possibilities is an even more profound truth. Intelligent life fundamentally changes the character of the universe. A lifeless universe is simply matter and energy following physical laws. A universe with consciousness is something else entirely. A cosmos capable of reflection, curiosity, creativity, and meaning. If Earth is indeed uniquely inhabited, then humanity carries an extraordinary responsibility to preserve itself not just for its own sake, but for the sake of the universe's ability to understand itself. Every scientific discovery, every telescope, every equation, every exploration represents the cosmos awakening to its own nature. And even if alien civilizations exist elsewhere, Earth is still a rare point of awareness in a universe overwhelmingly dominated by silence and emptiness. Our planet, small as it is, may host one of the few sparks of cognition in all of space-time. This perspective transforms Earth's insignificance into something approaching cosmic importance. The vastness of the universe does not diminish the value of life, it amplifies it. Against a backdrop of trillions of dead worlds, one small world filled with thought, emotion, and memory becomes precious beyond measure. And whether we are alone or merely isolated, humanity stands at a pivotal moment in its history, a species capable of destroying itself through short-sightedness or elevating itself through exploration, understanding, and compassion. The silence of the universe is not an answer but an invitation, a question waiting for a species brave enough to search for meaning amid the stars. As our journey through the universe reaches its outermost scales and loops back toward the tiny world where it began, we arrive at a perspective that is simultaneously humbling and breathtaking. The recognition that Earth, despite its vanishingly small size in the cosmic hierarchy, represents something profoundly rare, perhaps even unique, in the observable universe. It is the only place we know where matter has arranged itself into living systems, where chemistry has given rise to biology, where biology has produced cognition, and where cognition has blossomed into self-awareness capable of contemplating the universe itself. And yet Earth's story is inseparable from the vast cosmic forces that shaped it. Our sun, now in comfortable middle age, will not shine forever. In about 5 billion years, it will exhaust the hydrogen fuel in its core, swell into a red giant, and engulf the inner planets. Earth's oceans will boil away long before that, as the sun gradually brightens and transforms our once habitable world into a scorched wasteland. Long before the final engulfment, Earth will cease to be a cradle for life. If humanity or its descendants continue to exist, they will need to leave this world behind, migrating outward into the solar system or beyond. Mars, moons like Europa or Titan, artificial habitats floating through space. These may become future homes for our species if we survive long enough to master the necessary technologies. Eventually, however, even these worlds will not endure. Solar systems themselves decay over cosmic timescales. Stars burn out, galaxies merge and transform, and the universe grows colder and darker as its expansion accelerates under the influence of dark energy. If the expansion continues indefinitely, distant galaxies will recede beyond the cosmic horizon, disappearing from view and leaving only the remnants of the local group bound together by gravity. Over unimaginable stretches of time, stars will exhaust their fuel, black holes will evaporate through Hawking radiation, and the cosmos will drift toward a state of near-perfect darkness. In this far future, the light and structure that once defined the universe will fade, and only the faintest whisper of energy will remain. Against this sweeping timeline, the existence of life on Earth is a fleeting phenomenon. Humanity occupies a brief spark in cosmic history, a species that emerged only moments ago in astronomical terms, and that could disappear just as quickly. Yet it is within this brief window that we have the opportunity to imprint meaning onto an otherwise indifferent universe. For all its grandeur, the cosmos does not care whether stars shine or fade, whether galaxies collide or disperse, whether planets form or crumble. It follows the laws of physics without intention or purpose. Meaning exists only where conscious beings create it. And that is Earth's extraordinary significance, not its size, not its location, not its longevity, but the fact that it hosts minds capable of curiosity, imagination, empathy, and wonder. We are the universe becoming aware of itself, the product of stardust that has learned to ask questions. This awareness endows even the smallest actions with cosmic weight. When humans preserve knowledge, explore space, protect biodiversity, contemplate philosophy, or extend kindness to one another, they nurture the rarest phenomenon in the known universe: consciousness. Earth is a pale blue dot suspended in a sunbeam, as Carl Sagan famously described it, a world that appears insignificant from a distance yet contains everything we have ever known, every culture, every discovery, every moment of joy or sorrow, every life that has ever been lived. From afar it blends into obscurity, but up close it is a world of staggering complexity and beauty. Mountains rise from tectonic forces powered by the planet's molten core, oceans churn with life born more than 3 billion years ago, and forests breathe in harmony with the atmosphere that shields us. Every element of our planet, its magnetic field, its orbital stability, its climate cycles, its chemical abundance, has contributed to the delicate balance that allows life to flourish. That balance is fragile. The future of Earth's biosphere hinges on our willingness to protect it. Climate change, biodiversity loss, and environmental degradation threaten the stability of the very system that sustains us. Our cosmic insignificance does not absolve us of responsibility. Rather, it heightens it. If Earth is one of the few islands of life in an ocean of darkness, then the responsibility to safeguard that life becomes a sacred duty, not merely for humanity but for the universe itself. As we stand on this small planet, aware of both its tenuousness and its uniqueness, we face a choice. We can squander our brief moment, allowing fear, division, and short-sightedness to define our legacy. Or we can rise to the challenge of our cosmic reality, embracing curiosity, cooperation, and stewardship as guiding principles. The universe will continue its grand evolution regardless of what we choose, but only through our choices can consciousness endure. Earth may be tiny, fragile, and fleeting, but it is also extraordinary. In a universe filled with silence, it sings. In a cosmos shaped by blind forces, it dreams. And as long as there are beings on this world who seek to understand the stars, the universe will never be indifferent again.